today's live product update focusing on random vibration testing. Before we get started, as always, just a few housekeeping notes for this webinar. Lansmond is a member of the Physical Properties Testers Group, or PPT, which is a collective of specialized brands in physical properties testing. PPT covers areas such as tensile and compressive strength, torque testing, textile analysis, and real-world dynamics like shock and vibration. Alongside Lansmond, our family of brands include McMesson, James Hill, and Alluris. And to learn more about PPT and our individual brands, you can visit the PPT site or actually take a look at all the on-demand content that each of the brands have developed. And I will put a link in the chat box for your convenience. Many of you already know today's host, which is Eric Jonassen, Lansmond's VP of Technology. My name is Sharon, and I'm one of today's organizers, but we are supported by a dedicated team across the United States, Europe, and Asia. As always, we encourage you to ask questions. You can use the question box throughout the webinar to submit any questions that you might have, but we'll only address them at the end of the session, so feel free. The webinar is being recorded, and as always, you will receive the recording via the email that you registered with, and feel free to share it with anybody who might find it of interest and keep it for future reference for yourself. And with that, I'll hand it over to Eric.
Okay, thank you, Sharon. And I am quickly going to stop sharing my screen and share my camera. Sorry, I'm getting there. It takes a second for it to come up, but I just want to quickly, once again, introduce myself. Oh, I'm not sure why it's why it's blurry. That's not supposed to be the case. Let me see if I can change that real quick. Bear with me, folks. I apologize. That wasn't blurry a second ago, but it is now. So let me see if I can change it. Changing to no, it's not selected there. I'm 2 seconds, I'll be ready. Hi, why are you blurry? Sorry. There we go. All right, Sharon, can you verify that that looks okay? All right, I don't have it shared at the moment, do I? What a bad start, I apologize.
That's perfect.
Yeah, okay, sorry. All right. Let me get myself squared away. I can't even see myself anymore at the moment, but I'm going to introduce myself real quick. Eric Jonassen, back at Michigan State University for a live update, obviously, because of a little hiccup there, getting things going. But I am here once again to work doing some live demonstrations with a vibration system versus just sitting in an office and showing videos and slides and things. I'm going to run through some slides before getting to the demo itself. But I'm here at Michigan State. Previous live update we did, which was focused on sinusoidal vibration. I also spent some time walking around the vibration system itself to highlight kind of the key components of a vibration system. I'm not going to do that this time, since I assume some of the people have attended the previous one, and some of that detail is in the recording from the sine vibration demonstration. But from here, just because I have cameras set up right now, I can just at least point to some key components and kind of what the setup is that I'm using today, which over on this side, over here is the vibration controller itself. You can't see some of the detail, but some of the key interface pieces and components of the hardware, what we call our interface box, are down on a shelf there. Obviously, the GUI, or the interface that the user sees with our touch test vibration controller, is part of the computer system and set up here. I've got it angled my way because I also have another camera that I'm planning to use here to show what's actually taking place on when we start doing some of the testing, and then on the machine itself or on the table. So vibration system is in Michigan State is mounted down in a pit, which is a nice setup for loading and unloading and being able to walk closely to it and see and kind of get a little bit more intimate with the items that are being tested. So on the table itself, there are items on this table, right? They're for demonstration purposes, not for my demonstration purposes, but really for teaching demonstration. So they have a couple stacks of containers on here. The green guys over here are lighter. They're not filled. So there's a stack of 6 of these containers. They're not full. They're lighter as compared to these black ones. Same size, same number, heavier, lighter. The idea there is to show when we do some of this testing, the difference in what we would call column stack resonance based upon the weight of those loads. One will have a certain resonant characteristic associated with as compared to the other one. Lighter loads would be a higher natural frequency, heavier loads should be a lower natural frequency. We also have some springs on here. I've shown these in the past as well, but some springs down here, if I kick them, you see them shaking. Hopefully you can see those, and I'm going to show them in more detail as we move forward. But each of those springs is tuned to their own natural frequency. So I'm going to use all that when I demonstrate, even in the random vibration side of things, how things respond to the different types of random vibration inputs. Okay, so right now I'm going to turn the camera off, share my screen, or share my presentation screen, and we will get going. Okay, so today's webinar is focusing on random vibration. This is just kind of a quick little video showing random vibration and what it looks like. Basically, when we're running it, we're actually going to run some live tests here, but the idea here is a little bit different than in the past. Sine vibration, looking for resonance, product testing, sinusoidal resonant characteristics. Random vibration is more used to simulate environments. And in our case, in our world, my community of people I work with in Landsmount, we're talking about people that are dealing with cargo transportation. That's the environment that we're talking about. It's transport environment, and it's specifically transport environment as it relates to moving cargo around the continent, around the world. And when we talk about random vibration, just some kind of key characteristics or definition around it. Random vibration tests are intended as environmental simulations. I say that because I think that's generally understood. And it's not absolute, but most people use it because we're trying to simulate an environment. However, there's some certainly a number of caveats associated with that. It's not really full simulation of all the bad things or all the different types of dynamic things that can occur in an environment. It's more of a simulation of the frequency content that you will experience when you're shipping in a transport mode. And when if we assume that PSD profiles that we capture, for instance, from the field, and its intensity or their intensity is reasonable and accurate representation of the mode and condition of transport, then we can say 1 hour of testing would equal 1 hour of the represented transport motion. So what that means is when some of the questions that you typically get, that I receive and that people talk about at maybe different events and conferences is, how many miles equals 1 hour of testing? Well, in the absolute definition of things, if you go out and you measure 1 hour of vibration and you create a PSD, a power spectral density profile based upon that 1 hour of measurement, that 1 hour equals 1 hour of test time. That's what you would do. That's what you would use to simulate that environment. It's not 1 hour of the testing equals 500 miles, 1 hour of the testing equals 1,000 miles. It's time per time, basically, when you measure data. However, there is a broadly accepted methodology for what we call accelerated random vibration testing. which includes basically, and the way it works is it reduces the required test time by increasing test intensity. Could be a whole nother webinar all by itself, is how to apply this formula. So I stuck the formula in here. This is generally accepted formula that is used in, across the testing community, I would say, and even in the industry standards. And basically what it says is if I measure an environment and I record 20 hours of transport, and I create a PSD based upon that 20 hours of transport. If I want to simulate that 20 hours of transport in a 4-hour test or 5-hour test, what do I need to do to the PSD intensity level to basically make that a valid, deliverable? And so there is a testing methodology that basically says, okay, well, if you want to do that, you can reduce the amount of test time by increasing the intensity of the data that you collected by a factor of X. And generally speaking, when we use this formula, we don't want to ever exceed a 5 times rule. Basically, that says if, listen, don't accelerate things any more than 5 times. So that if you're recording 20 hours of transport, you wouldn't want to reduce the test time to anything less than like 4 hours. Because if you did so, you risk increasing the test intensity to something unrealistically high. Because the formula doesn't account for that, right? It's just math. But the risk is if you try to, let's say simulate 20-hour test 20 hours of transport in 1-hour test, which is even more kind of time compression, you would have to accelerate that test level or increase that test level so high that the intensity would be so severe it would be unrealistic. You would cause probably damage the second to your whatever you're testing by hitting the start button on your machine. So there are some rules associated with that application of that formula, so that you are cautious about and conservative about not overdoing it on your test intensity. So PSD profile. What are they? I've said in even the previous webinar that I hosted on more of the random vibration testing applications, I think of PSD profiles as like the signatures or fingerprints or identifiers of transport modes, right? So the shape of that curve on the right-hand side, that green curve, and the intensity of it speaks to what the mode is. And as you look at these profiles, what I just, the identifier that just showed up there, you see on that curve, there are peaks and there are valleys, or peaks, troughs, high plateaus, lower plateaus, but there are peaks and valleys. And so those peaks tend to correspond to something unique about that transport mode. And in this case, what I'm showing is the ISTA air ride profile that is referred to in ISTA's procedure 3H. Well, what does that mean? Well, that first peak on that green trace, you can think of as being associated with the suspension, basically the airbags, the suspension of the truck. The next peak that you see on a profile like that is typically associated with wheels, tires, rotation. Obviously, you can think of trucks, tires, or car tires rotating as they're going down the road. Obviously, the speed can vary when things are being transported, but over, let's say, a long haul transport across continent or long journey, the speeds tend to be in a certain frequency range, that's associated with that vehicle moving down the road. And then the third peak, which is a lower peak, is usually assumed to be associated with more of the rigid structural members associated with a truck trailer, maybe a container. But it is associated more with the structure of the transport vehicle itself, the overall structure. But the big inputs are normally for transport associated. The low frequency inputs, like the one on the left there, are associated with vehicle suspensions, whether it's air ride trucks, leaf spring, steel spring, leaf spring truck transport, or even some of the suspensions that might be on rail cars, which are basically steel springs. Their suspension is springs. So that is that's kind of a fingerprint. So that if you see data like this, for me, if I see somebody's data, raw data, I can typically look at it and identify how it was transported, or at least where that data came from, what type of a vehicle or transport mode. Here's another profile. Okay, so this is an actual random vibration profile in ISTA's procedure 1G. What the 1 series test procedures and within ISTA stand for, or basically means non-simulation integrity tests. So this is a PSD profile. It covers the frequency range on the x-axis, left or right, frequency range of 1 to 200 hertz. But the shape is kind of flat, right? It's a kind of a flat profile over a wide frequency range here. You can almost think of that when you see these kind of profiles as being like maybe kind of like the equivalent of white noise. It's not apples to apples. White noise is a different frequency range that's audible versus the transport frequency range, which is lower frequencies, and typically part of that is inaudible. But it's flat, just like what you would expect with like a white noise profile that you might listen to on a sound machine. So this profile doesn't really simulate anything. It's just kind of think of used for integrity testing. So it's included in a number of test procedures, and quite frankly, where this came from, once upon a time, this profile was really a combination of the ASTM truck and air profiles. This is going back 30, 40 years ago, really basically combining those two profiles and taking the high peaks across both of those profiles and saying, let's call that a test. Some people used to refer to it as the truck air vibration spectrum. And it was, all enveloping. And so it's, as you can imagine, it would be, in this case, a very robust test input. And it didn't simulate really anything that's you would expect to see in the real world. But it offered a pretty robust input. And the idea there is if you can pass it, you can pass that test, your packaged product, or even just product testing. If you can pass that test, you should have high confidence that you're not going to experience any problems transporting your goods through the supply chain. The problem with profiles like that is well, what if I fail? What if I fail the test and I was using that test input? Does that mean I would expect problems in the supply chain? That's a risk. So these aren't as broadly used, these types of profiles, when people are really wanting to zero in on trying to get closer to reality of what's going on in their supply chain. But these type of profiles do exist, and it's not in those examples used for simulation. PSD profiles that we see in ISTA, ASTM, ISO, MIL standard test specs. What do they address and what do they not address? And so, what I say here is they address kind of constant normal. I don't mean normal necessarily in the statistical sense, but the constant kind of normal, quote unquote, traveling down the road, energy and motion. And so what that means is, when things are just kind of going down the road for long periods of time or down the rail, this is what it can look like. This has got audio. I apologize if you can't hear it, but you'd be able to hear it when I share the recordings of this. So there's intermodal truck and there's intermodal rail. And there are sounds associated with both of these videos. They're different sounds too. Truck is more harsh and severe as compared to that rail profile. But that's kind of what PSDs are used for, simulating, is that energy, buzz, motion that you would expect as things are moving from point A to point B. And it's not geared towards being necessarily overly severe or overly gentle, one way or the other. It's kind of, give it a dose of energy for some period of time, usually in minutes, obviously more like hours, to see if I'm going to have any issues associated with things like abrasion, fatigue, scuffing, things that we, damage that we more commonly associate with vibration. What they don't address, I would say, they typically do not address extreme transient transport dynamics. And what that means is, all right, this next video is going to show also video from inside a container, unit loads going down the road, and then all of a sudden they cross a bridge abutment, or where they cross a bridge on the freeway. So there's vibration, and then all of a sudden, kaboom. You see what happens. These loads jump, going down, vibration, rock and roll a little bit, boom. Big input happens. Those loads actually jump so high, quite frankly, from that rough road, is that they hit the top of the container. And that, is that vibration? Do we mix that into our vibration test? Would we like to mix it into our vibration test? Maybe, but we don't. I would say 99.9% of the vibration tests that people perform doing random vibration, ISTA, ASTM, MIL standard, ISO testing. That's not part or included in the approach to those random vibration profiles. There's been a lot of talk about it. There's been talk, I would say, over the last 20 plus years of how to account for some of that, but it's really separate. And the answer is, well, there isn't an answer yet. Some of the things we talk about is shock on vibration or transient on vibration testing. Is it a standalone extreme input that addresses things like those bridge crossings, rail crossings, potholes? But we don't blend them in typically into a random vibration test. Even if they are in there, in the SA data that comes from the environment, they typically get averaged out because you mix it in with data from a 1,000-mile, 500-kilometer transport. If that happens a couple times in transit, and you mix all that data together, those big inputs tend to get averaged out. So it's a question, how do we address those? But for the sake of this kind of conversation, we don't, those are not part of the typical random PSD profiles that we all use in our most common testing. So when we program, right? So PSD profile, when we program breakpoints into a vibration controller, I'm going to show you kind of what that looks like. Okay, so this is the PSD breakpoints for the newer, ASTM D4169 air profile. 6 breakpoints. You see them on the left, frequency versus PSD. So basically what we do is we plot those, right? So over on the right-hand side, you see 6 points on a graph. That is a frequency versus PSD plot on the right-hand side. And if I plot all 6 of those points, there they are. Not very exciting, but that's how we start by creating our test profiles on our vibration controllers. And basically what we do is we connect the dots. We connect the dots from those breakpoints, and there's our PSD curve. And so that shape of that curve then has a test intensity associated with it. In this case, the GRMS for that test intensity is 0.29 GRMS. Okay, so easy enough. We can take those PSD, 6 PSD breakpoints, frequency versus PSD breakpoints, and program them in our controller, which I am showing here. Okay, one was in Excel. Now I can just enter those breakpoints in a controller. But what's key or critical here, just to understand, not to change anybody, be concerned with changing these things in their controller, is how a vibration controller uses those breakpoints to run the test. And so really that key criteria is right there in the frequency range and the number of analysis lines. And so what that means is the vibration controller needs to understand within what frequency range am I going to be running my test moving forward, any testing moving forward. And there's reasons why you might change that. You see in this example, there's 4 selections, 165 hertz, full scale kind of range, 330 hertz, 660, 1300. In our world, in the transport, cargo transport simulation world, most of the industry standard PSD profiles that we use go out to, maybe on the high end 200 hertz. So in our case, we're going to say, listen, on the controller side of things, I'm only going to look between 0 and 330 hertz for the range of frequencies that I'm going to control within. And then what the analysis lines means is basically it says, okay, if I have a frequency range from left to right when I look at these PSDs that I'm going to focus on, 330 hertz, I'm going to slice that up into what are called like bins, right? Analysis bins, because that's what I'm going to use to control my vibration controller. And so I'm picking in this example 330 hertz for the range and 900 for the number of analysis lines, which basically gives me, if you look down at the bottom, let's see if I can show you here on my, yeah, down here, right there. The resolution says 0.367 hertz. What that means now, what that means, you know, from a trying to understand things is if I put that PSD back up there, which is really only made up of 6 points, I'm going to look at that plot, and then down at the bottom of the screen, you can see what I did here is I've basically plotted a point at every 0.367 hertz. And so it's really, I've diced that up into 0.367. There's 900 points, believe it or not, there on the bottom of the screen. And what I'm going to do is if I draw a line up basically to the PSD curve, says I'm going to basically, and I'm only doing it for like the first 10 PSD points because I can't, nobody wants to sit and watch me do 900 of those. But I'm going to apply or focus on controlling along that line. Forget the 6 points, but think of it as the curve at this point. I'm going to slice that into individual control points along the PSD curve, whichever curve that might be. And I'm going to do control. You know, I'm going to do math on each of those as the test is running. So what that really looks like, now what you're seeing here is real data from a controller, just exported data at any given time. Those are the 900 points along that curve as the controller is running. And those things change every couple seconds, you know, less than a couple seconds. At any given time, this is telling you what the vibration intensity is being controlled at that breakpoint. This is what's being controlled at that breakpoint, that one, that one, that one. You can see dot, dot, dot. They're all trying to control at each one of those analysis lines, all 900 of these orange lines. They're trying to basically achieve that gray line, the demand line on average. So, but it's on average, remember. And so sometimes those dots are high, sometimes they're low for each of those analysis lines. But there are 900 different control math taking place at any given time across a PSD. And so those are dots, right, at each of those 900 lines. But basically then, if you connect the lines or connect those dots together, that's what you see on a vibration controller when you're watching it run in real time. And it moves, right? Or I mean, it kind of jiggles around. The line basically stays on top of that gray line. In this example, the orange line stays basically on that gray line, but it dances. At each of those frequencies, it dances a little bit above, a little bit below. But that's, again, remember, it's because it's changing. It's a random input, sometimes a little bit high, sometimes a little bit low, but always on average doing what that gray line is. So that's kind of the method to the madness of how you run one of these tests. And then what's also important to understand is when we look at PSD profiles, they're plotted in log-log format, meaning that the y-axis uses log scaling and the x-axis uses log scaling. And so each one of those major divisions is, means that there's a 10 times factor in the amount of equivalent, or not equivalent, but of energy. So back to this one. In this example here, remember, and this is log scale. So there is 10 times the amount of energy at that frequency, which is 2 hertz, as compared to that frequency input, which is 1 hertz. So it's a scaling thing to understand when we look at these log scales, and it's the reason we show them that way is to allow us to a more clarity in seeing across the overall intensity at individual frequencies, because if you do it in linear scale, it becomes a little bit maybe harder to make sense of it all. But here's what it looks like. If I do linear scale, just in the y-axis, in the amplitude, now you can see my scaling has changed. This gives you an appreciation of how much low frequency input there is, let's say, in the new air profile as compared to the higher frequency inputs. So, because I'm linear scale now, you see that, right? You see that here, there's almost 10 times the amount of energy is here, and there's more than 10 times the amount of energy as we get out to, out to the 40, 50, 100 hertz, 200 hertz. There's not much energy at all. Most of the energy content in this example is associated with the low frequency content. And now if I change it to linear on the y-axis and linear on the x-axis, you get an idea of, once again, where most of that energy in a PSD profile is associated. Really gives you, kind of apples to apples kind of comparison of on the X scale, and in this case on the Y scale of the intensity. So new air profile, most of the energy in that test happening down in low frequencies. 2 to 10 hertz, something like that. It's low frequency, not high frequency. So that log, PSD on the left-hand side is equivalent, or it is the same, that's the same profile on the right-hand side, just in linear scaling. So two different ways of looking at the same profile, but give you different ways of appreciating where the energy is, basically meaning where, at what frequency am I experiencing most of the energy input, okay? So here's a couple other examples of that. So we can compare like mode, I would say like mode profiles. In this example, okay, a little bit harder to see, right? Because now these are linear on the Y and linear on the X, but these are comparing two different truck profiles. The dark blue one here, which is this guy here, that's the old ASTM 4169 truck profile that was updated back in 2016. So think of it as pre-2016. That's what it looked like. And then the blue one, the light blue one here, that is the one that replaced it, or that it changed to in 2016. And so this gives you a way to literally compare without, again, trying to understand scaling. This is linear scaling, the difference. And so with the new profile, there's a lot more low frequency input, which isn't necessarily a bad thing, but there's a lot more low frequency input associated with suspension and a lot less input in the mid frequencies. So this is 10 hertz. So, out to about 20 hertz, maybe even out to 40 hertz. There's the old profile had way more energy than the new profile. And what are the implications of that? Well, I'll show you when we get to the live demonstration here in just a quick second. But there's implications absolutely associated with that change. And then one last comparison. This is comparing like modes also. But now these are the air profiles. So the air profile in ASTM was updated in 2020, and that was based on a big effort. In 2022. So this says 2020, but that should say 2022 when we changed updated the air profiles, and that was based on research. There was a lot of effort that went into that, and a lot of measurement that took place, not just by certain individuals, but by a work group within ASTM that said, let's take a look at the air profile. Does it need to change as well? And so we did change it, and you can see the differences. And this is pretty significant. So this lighter red profile is the older air profile that goes all the way up to 300 hertz, and it has pretty darn high intensity, throughout that whole frequency range, as compared to the new one that went into place in 2022. And that's not an insignificant, that's a real kind of dramatic difference in seeing the difference in the amount of energy. A lot more higher frequency, mid to higher frequency energy in the old profile that is not part of the newer profile. And it wasn't arbitrary just to lower the intensity or the severity of the test. It was to follow what we all believe is the right thing to do based on data that was taken from air transport measurements, not just jet aircraft, but even turboprop. So that's a way of visualizing those differences. And so for the demonstration that I'm going to do here today, I'm going to run a number of sequential tests with these loads that I have set up on the test system, two column stacks of containers as well as the springs. So I'm going to run the older ASTM truck level 2 profile for a minute. I'm going to run the ISTA 3H steel spring profile, which is also basically the same profile that's referred to now in ASTM 4169 at the mid-level test. I'm going to run that so you can see the different responses. Going to run the air ride, ISTA 3H air ride truck profile. You can see again differences between all three of those, right? As far as what they look like from a test profile, and then we'll look at does that have any implications on what's being tested on a machine. The ISTA 3H rail profile is pretty significantly different. The new air profile, ASTM 4169 2022 air profile. And then I'm just going to play around. I've got a couple PSDs in there where I've actually created my own profiles that have kind of a flat profile. But what I've done is I've increased the intensity within the frequency range where the stacks, those two stacks of containers on the table, where their natural frequencies are. So I'm kind of faking it and saying, listen, I'm going to run a test profile, but I'm going to really push those two stacks. I'm going to increase the energy where they like to respond and shake. So you can see what that looks like if someone does want to make more of an accelerated test plan. And then this third one, or excuse me, this one with the three peaks at the right-hand side. Remember I showed, and I will show you on the cameras, but there are three springs also mounted to the table. Each of those three springs has a natural frequency, depending on the spring mass setup there. There's a heavy mass, a middleweight mass, and a light mass on the springs, and each of those has a unique natural frequency. So what I'm doing with that blue profile that I made is I'm not only exciting the two stacks of containers I have on the table, but now I'm going to put energy in to excite those springs, very specific to excite those and push all of those things at their natural frequencies as part of a random vibration test. And then lastly, I just kind of say, I don't need to create a profile to shake from, let's say, 1 hertz all the way to 200 hertz. If I want to just focus on the natural frequency range, or a frequency range that challenges my loads, I want to really focus, I can do that. And so in this last example that I'm showing there and that I'll run is I'm going to just run a test between 6 and 11 hertz. And you'll be able to see what the response is, and you'll hopefully through all the demonstrations, you'll also be able to hear the differences as well. And I think you will, because you'll be hearing through my microphones that I have in my earbuds here. So with that, what I'm going to do is I'm going to switch my computer, stop sharing my screen. I am going to turn my camera on. And I'm going to leave this camera on. I'll get out of the way. And then I'm going to turn my camera on here on my phone, which I have pointed at my vibration controller. So I'm going to show you once again what's programmed into the vibration controller is really a test, what we call a test queue. Okay, it's a test queue of all those profiles that I just kind of walked through and showing you on the screen. There's a number of profiles listed here, from that older ASTM truck profile, the ISTA steel spring profile, the air ride, the rail, the new air profile. They're all in what we call a test queue, and they will all run sequentially. I have them set up to run for 1 minute each, just kind of as a quick demonstration. So I'm going to do that here in a second, start that. And I've got this guy on a swivel. I'll come back to the controller in a second, but and you can see it from kind of the zoomed out perspective, but also the somewhat zoomed in or focused perspective. So I hope you can see, but again, what you'll see throughout this and here is stack of containers light, comparably light, nothing much inside these, any of those containers. Same containers, but heavier load. These are heavier. So this whole column has a heavier mass than this column. So we would expect the responses of these to be different based upon their weight characteristics. And then I've got these springs down here, these springs, 3 different springs, 3 different masses, big mass, middle mass, light mass. Each of those, because of the mass, spring mass relationship, has a different resonant frequency characteristic associated with it. So I'm about ready to start the test, make some noise. Hopefully you hear it. I'll try to stop talking when it's running. But the first thing we're going to do, we will run the old ASTM truck test. And what you'll see is that, well, see and hear, I'm going to start it. Table comes up. You see the shape of the profile on the controller. And now you start to see a white signal. That's the control signal. Those are all those little jaggedy peaks and valleys. Those are the 900 points, right? Connecting the dot of 900 points as we're running that test. And hopefully you can hear it. You can see them jumping. Try to get closer. They're chattering because they're jumping. They're being excited at their natural frequency, which for both of those is in the 6 to 10 hertz range. 6 hertz for the black stack, 10 hertz-ish for the green stack. And because the profile we're running inputs energy at 10 hertz, it's this flat line. It's putting in a lot of intensity at that frequency range, so it's making those stacks jump. Now, we're switching to the newer ISTA 3H profile, the newer ASTM truck profile that has a shape, more of a defined shape associated with it. Still get a little chatter, but because we don't have a flat line here in that 6 to 10 hertz range or an area of high intensity, it actually dips down. We have less going on. We have less chatter taking place, meaning less hopping or response from either of these stacks. There's a little bit, but not much. Not much. So we're not exciting them as much. Is that good or bad? Depends on your perspective. But the idea here is we're trying to simulate reality. So I would say it's a good thing, right? We're not over testing because we're not driving artificially high with energy that wouldn't be experienced in that mode of transport. And you can audibly hear the difference between these guys with their responses. Now, controller is shifting or changing to what we call the air ride transport. It's a subtle difference, but there's a difference. It's a lower suspension frequency associated with air ride transport because it's a softer ride, better ride. The idea for the most part is that air ride transport, truck trailer transport, is a much better ride than leaf spring. And I would have to agree from my experiences, either measuring it or working on projects that focused on comparison, it's better. It's more gentle. Might be hard to tell. You still hear some chatter, a little bit of chatter, not a lot. You see more displacement, more movement. So you might look at that more movement and think, oh, that's more violent, but it's actually not. Unless you have a natural frequency at that frequency, which is 2 hertz, which most items don't anywhere close to that. So the idea of the suspension moving, air ride suspension moving at 2 hertz is a good thing because think of like trying to catch a big, heavy bowling ball that's thrown at you. What you do to cushion that is you move, you displace. So that's what an air ride suspension does, is it moves more, and it displaces more to help attenuate that energy from being, any energy above that from being added into your packaged product. This is the rail profile. This is the 3H rail profile, the most gentle of any of these profiles that are being run here. Low GRMS level, much less significant than anything that we've run here. And showing what that looks like on the screen. There's not a lot of any upper frequency characteristics associated with that, just this low frequency suspension input here. Now, I will say, and you can see here, even though it's all low frequency, it's still not, it's comparably less low frequency than any of the truck profiles or the air ride profiles. That's just an old profile. It needs, in my opinion, needs updating, and there are some things that I'm working on myself to, with even the rail side of things, to go measure that with the idea of seeing if we need to update either the ASTM 4169 or any of the ISTA rail profiles to make it be more representative. But right now, it's by far the lowest natural, or not natural frequency, but the lowest GRMS intense profile in the vertical direction. That's a key word here. Okay, here we change one more time. Now we got the air, the new ASTM air profile starting out. Mostly low frequency on this end, but we've got a little blip of high frequency energy out here in the 60 to 200 hertz range. You can't hear it quite yet, but in a second you will, as it says, I need to bump this white signal up and get it to the green range. Don't know if it's obvious or not, or evident, but you can start hearing kind of a higher frequency ringiness associated with the system that is associated with that bump out there at the high end at that 60, 50 to 200 hertz range. It's not a real big amount of energy, but you hear it. And quite frankly, it sounds right. You know, if you do that kind of a lot of air travel or a lot of air transport measurement, you say, yeah, that makes sense. Still a relatively gentle, much more gentle than the old ASTM air profile. And again, you could argue that or question that, but I tell you, I'm completely confident in it because it was based on lots of measurement data and observation of the air transport environment. Okay, now a fake one. Flat profile out to 100 hertz, but I've added this bump in the 6 to 10 hertz range. This little segment of energy. Why did I do that? Well, because that's where those two guys like to think. Different frequencies. You can kind of see the black one shaking differently. They're both kind of like bubbling or percolating differently. They're responding differently based upon that energy, but it's all being input there and it's focused, and I'm stressing them by running a profile like this. I'm stressing them, maybe artificially, right? But I'm doing it at their natural frequency because I'm trying to get, find out if that natural frequency, the response at that frequency is going to cause me problems. And so I'm forcing them to dance more than they would necessarily in the real world by adding energy. And then this one, I've changed. Here we go. We're about to start this one. Now I've added 3 more peaks here. And these 3 peaks are associated with the natural frequency range of those springs. So here we go. You might be able to hear it. Each of these guys is shaking, and they kind of get excited randomly. You can see each of them. You might be able to hear them more than you can see them. But I'm able to add big energy inputs at each of their distinct natural frequencies, all as part of this PSD that I can play around with and program to tune specific frequency content if my goal is to seriously challenge each and every one of those, the stacks and the springs. I can do so. And then lastly, weird looking profile. Get rid of all the noise, or not noise, but the frequency content from 1 hertz to 6 hertz and from 12 hertz to 100 or 200 hertz. Get rid of that. I'm just running a test profile from basically like 6 to 10 hertz from that point to that point, driving it hard. still getting that response from my stacks. What you might not be able to hear is all the other rumbling frequency input that would be driving through the table. And you would be able to hear it. You don't hear the springs anymore because I'm not exciting those springs. That one's jiggling around a little bit. It's lateral instability. But you don't hear those springs responding at their natural frequency, and you don't hear the table shaking at either really low frequency, the rumble, or at the higher frequencies associated with the wheels, tires spinning. It's just focused on exciting at the products or the stack's natural frequencies. Cut to the chase kind of idea. Let me focus right on the content, the frequency content that might cause me concerns or challenge with my packaged products. Okay, so where am I? 11:50. I'm done with my presentation right now. I am happy to answer any questions. I will, the caveat again, I keep telling everybody that I talk to, boy, these are hard presentations because random vibration is something that is a semester long content, course, and probably more than that, quite frankly, but you could talk for hours. And actually I like talking about it, but it's hard to figure out how to address it in a 1 hour, 45-minute, 1 hour session. So tried to touch on it. I'm happy to answer questions now, happy to answer questions moving forward as best I can associated with this. And maybe with new ideas, adding additional courses where we can get into detail. So Sharon, if you're there, let me know if I have any questions.
Yeah, Eric, there's one question already, so I'll kick off with that. But just a reminder for everybody else, if you have any questions that you'd like to have addressed right now in the webinar, please add them into the question box right now. So I've got a question. A common practice that I've seen in the food industry is to test a layer of cases instead of a full pallet of product to save on wasted product. What issues do you see with this method? Are there any concerns when the cases are tested directly on the vibration plate rather than on a pallet as they are normally shipped? I mean, columns stacked per layer.
Yeah, so good question. I don't know if you can see this. Yeah, you can. This was on the table yesterday. They use this for a demonstration as well, right? I took it off because it's not very exciting and it just adds yet another thing on the table here. This is another column stack with weight inside these containers, but they're strapped. They're strapped together. They're unitized. And so when you unitize a load together like this or on a pallet load, it becomes a big, heavy mass. It's different than would be an individual one of these guys or individual ones of these guys in a column stack where they're not bound together. The natural frequency of this unitized load is very low because it's one big mass that's unitized. The natural frequency of these guys, these are heavier than these guys. So these are the natural frequency of this is still lower than this, but higher than that because there's a relationship when you talk about natural frequency of a spring mass system is basically you can think of as bigger, heavier items, lower natural frequency, lighter things, higher natural frequencies. So if you're talking about testing individual layers or individual packages, some of the trade-offs. If you ship things unitized, it's good. I would say it's going to be a comparably better ride from a vibration perspective because it's unitized. It's big. It's heavier. It's going to do better in transport than the individual packs. The other thing that you don't get when you, at least if you're talking about individual layers that you don't get, a big concern, now these are plastic containers on here, but a big concern if you're shipping corrugated, or even maybe plastic, is something that's called dynamic compression. So as a vibration, vibrations occurring going down the road and you have a stack of packages or loads, especially if they're not unitized all that well, is they might respond individually, just like these are. Their stack is if I had slow motion, you would see that It's like expanding and contracting as almost like a spring itself. And so what happens is they're bouncing on top of each other. And if they bounce, depending on how heavy they are and how much separation and what the impact is between each other, it's what we call dynamic compression, where it's stressing the materials of the different layers. And so if you're testing individual packages, you're not accounting for that part of it. So it might in some ways experience more harsh of a ride, test ride all by itself from the energy input. What it's not getting is the energy input from surrounding packages and materials that it would likely, in many cases, it would likely experience in the real world. But so I would think, even a column stack test like these that you see here, even if it was corrugated, that's likely, I would say, not that it's been a while since I've worked strictly in a laboratory, but in that case, probably more severe testing inputs than the unitized load inputs. So you have to take that into consideration when you're assessing the results, especially if it fails. What does that mean? But if it passes column stack test, I would say it's probably a pretty good indicator that vibration is not going to be an issue for you. Long answer.
Thanks, Eric.
Yep.
Next question. How can we isolate these random vibrations on a long distance transit, as our products are not intended to operate with these random vibrations?
I don't think I understand. I don't think I understand the question there. And I don't know if that person, I'll try to throw an answer at it, but if they want to explain a little bit further, so be it. But with all that frequency content that we showed there, say 1 to 200 hertz, in the ideal scenario, you would understand, like this example. Let's say this has a natural frequency, this column stack of 10 hertz. This one had a natural frequency of, say, 6 hertz. Or it could be a package of apples. They have their own natural frequency characteristics, where they like to shake. You obviously, in some of these profiles, let's just like this example here that I had on the screen. Now, this is not a real profile, but if this was a profile that was representative of some weird transport, I'd be asking for problems shipping either of those stacks in that environment. So I would want to do something to change their natural frequency characteristics, whether it's by changing the load, how I stack, do I unitize, and that certainly translates into the bare product, the product design. The more you know about your product, the better you can then design packaging to mitigate allowing any of that kind of bad energy that you might expect to see in transport from getting into and through the packaging into your product. But it kind of takes an understanding of your product, the packaging materials, and obviously the expected inputs in supply chain. And there's only so much, and sometimes you can change all characteristics associated with each of those. You can tweak the product design. You have the ability to tweak or design your packaging. Most people don't have the ability to, change what's going on in the transport environment. You can change the modes of how you transport things, but you really have don't have much of an ability to change how a train rides and how a leaf spring truck trailer rides. You don't have the ability to change that, but as long as you understand kind of the fingerprints of where the energy comes from and the intensity of what that looks like if you're going to ship by truck, there are things you can do to the product and the packaging to try to mitigate that. That was my answer.
Thanks,
I hope
Eric.
it was relevant.
Then the next one is, what method do you suggest for unitizing cases?
That's another one that I don't know that I'm sure I understand the question. Sorry.
That question is a follow-up from the person that asked about what's your opinion regarding the flat packed testing?
Okay, so yeah, I mean, with unitized loads, there are things like column stack loads, and there are interlocked loads, meaning, you know, do we, like these guys, do we stack them all in a column like that, or do we change them to be like this, you know, turn 90 degrees, and so you, if it was corrugated cases, so they're more interlocked, and they act, you know, if it's more interlocked, it even, you know, my experience is that it's more of a load locking configuration. It's going to be stiffening. It's going to be a more robust brick-like scenario if packages are interlocked. Now, is that, you know, there might be a lot of reasons why you wouldn't want to interlock, because maybe because of the footprint of the corrugated or shipping containers, secondary containers wouldn't allow you as much space utilization on a pallet load. But from a robustness and durability, I would say interlock pallet pattern is better than column stack. And then, you know, that gets to the whole idea of unitization. So that's just on stacking things, but how you then hold the stack together with banding, strapping, film, stretch films, what's the right film, the right gauge, the right number of wraps, all of those tertiary packaging components can help, you know, with the performance of how well it's going to do in that mode. And you can, quite frankly, you can stiffen a load or soften the load based upon what type of secondary packaging you use. Do you use a, you know, certain type of gauge of film material that's stiff, or do you use one that's soft, you know, and you can, based upon what the key characteristics are, you can make the load more compliant, or you can make it more rigid and stiff. And so it's back to, is one better than the other? Is a stiffer load better than a more compliant load? It depends. Depends on what your mode is of shipping and where the, you know, the resonance of the column or of the unit load lines up with the unique characteristics that might be in the supply chain. Like a leaf spring profile, if I go back to my test queue and I look at, let's just load this one up here. If you can see this on screen, you know, this is pretty normal. I would say normal for a shape of a truck, leaf spring truck profile. So if my unit load, you know, this is 1 hertz, 2 hertz, 3 hertz, 4 hertz, and then it drops down. But the key low frequency content is in the 3 to 4 hertz range. And then it drops a little bit, and then it comes back up at like 16 hertz. You would not want your unit load to have a resonance. You would not want it to bounce, in the 3 to 4 hertz range, nor would you want it to bounce in the 16 hertz, 16 to 20 hertz range. You'd want your resonant frequency characteristic to be of the load to be in this valley, not the plateaus or the peaks. You'd want it to be in the valley. That's one of the ways you would use, you know, the characteristic fingerprint of the real world transport environment to say, I can't change that. I'm going to have to deal with that. So if I have to deal with it, I would rather design my system to respond in the areas of comparably less energy input, if that makes sense. Because I can't avoid it. I gotta ship it. I gotta use leaf spring trucks, but I'm going to try to say, give me a natural frequency in the, you know, 6 to 10 hertz range versus anything outside of that range. And that would be one way of dealing with it.
Thanks, Eric.
Yep. Mm-hmm.
I've got another question. What is your opinion regarding a product fixed to the pallet using screws and a metal plate rather than placing the product on foam? Which case will face less severe vibration considering? And then it said, adding to the question, both cases have strapping present outside the box.
Tough one, I guess, you know, meaning tough to answer because I don't quite understand. I apologize the question, but all of that, those kind of questions depend on what the natural frequency characteristics are of the product and of the packaging or lack thereof, and then how it's going to, how durable is the product. If it's a fragile product, which you have to determine through product testing before you ever consider putting on a pallet or putting it in a package or on foam on a pallet, you have to, how sensitive is it? Maybe it's super robust, you don't have to worry about vibration. If that's the case, you don't need foam, you don't need cushioning. But if it's fragile, it's got natural frequencies, and it's susceptible to shock, very likely are going to need some type of protective packaging, meaning cushioning, to help it get through the supply chain. So it's hard to say which one of those is better. Obviously, one's better from a cost perspective. If you don't, nobody wants to use foam or cushioning if you don't need to. But it's too hard to say which one is better because it depends on what the product is and how fragile the product is. If you can get away without it, don't use it. But you have to prove that, I think, right? You have to prove that through product testing, somehow of characterizing the fragility of your product from a shock and vibration perspective is what I would say.
Great, thank you. And I think this is the last question we have is, I noticed on the video, the data loggers were on top of the unitized load. If you wish to generate a PSD profile for a specific journey, would you place the data logger on the top of the load or at the base? Would the top amplify the natural frequency?
Yes, it would change it, likely amplify it. So yeah, that's somebody's got a keen eye there. What they don't know, or you wouldn't know from looking at that video, is there were data recorders on the floor of that container, mounted, so literally mounted rigidly to the floor of that container. It was an intermodal container. There was data recorder mounted to the pallet, the base pallet. There was pallets stacked too high inside the back of that container throughout the whole container. So there was instruments on the floor, instruments on the pallet, on the base of the bottom pallet, and then instruments on the base of the top pallet, and then there was instruments in some examples on the very top. And it wasn't really even because they, that was it was more from a storage perspective to put them there. In that example, it was too hard to hide it, but it was there, it was valid, it was measuring things. But yeah, I would never use that prime measurement. It was more to understand the amplification, meaning if I have an instrument here on the table, let's just say this is the floor of a truck bed or an intermodal container. I want to know what's the input vibration. Then I want to know if I have an instrument on a pallet or a sensor on the bottom pallet, what's the response of that pallet to the input. And then if I have another pallet up here with another load, I have another instrument here to say what's the input, response number one, response number two. So I can understand the transmissibility or the amplification or attenuation that occurs when shipping through that environment. In that video, those were pallet loads of paper towels, which you can think of as, that's the product, but you can quite frankly imagine that that's a soft, compliant load for the most part, adds softness, almost like cushioning, right? But what does it do? What does that mean? That does it, even with all that, you think of it as cushioning, but does the cushioning have the product almost have its own natural frequency response, so that it actually, because of the mode of transport, some of these peaks and valleys, does it actually act like a spring and make the inputs greater, the response greater at low frequency? And if that's the case, which you can tell in some of those examples, if it's like a trampoline, it's not really scuffing and abrasion at that point, but it's a trampoline, so that when a big input happens, it jumps so much that it jumps back on the rolls of paper towels and crushes the cores or crushes the paper, or it hits the top of the container, which it did in those examples, because it got launched into the top of the container. So it was important, in that study to understand a number of different locations and a number of different containers that were shipped from the East Coast to the West Coast. Inspect, those loads inspected. Same type of approach used to ship a number of containers back to the East Coast, basically to characterize a very specific supply chain route and understanding the full input to response perspective in multi degrees of freedom. Fun project. So I hope that answered the question.
We seem to have acquired new questions, so I'm just going to read them to
Keep
you.
going.
So, what profile do you prefer to use for pharmaceutical devices in terms of packaging?
That's a good question. There's starting to become some familiarity between, or commonality between the ISTA and ASTM profiles that are used for truck and air, I would say. I'm involved in both. I'd probably say I am more involved in ISTA than I am ASTM, and I've been much more involved in proactive research that's taken place within ISTA. I've personally participated in that, going out and helping with certain measurements, and I'm just aware from my involvement within ISTA of other people going out and making those measurements to help, either develop new or drive changes to existing profiles within that organization. So, there is one significantly better than the other. I just know from my awareness and the participation of people that from across wide swath of industry, including pharma, biological pharma. I'd say the ISTA profiles serve as a really, I would have good high confidence in those, the foundation of those profiles. Now, the profiles, I would say, another one of these caveat things is, remember the test profiles within either of those standards organizations are typically, at least in the ISTA 3 series and even ASTM, they're probably accelerated at some level, considered accelerated. So you got to be careful about that, because they're accelerated and they say, it might say you run this test for 2 hours, maybe 3 hours, and that's the test, and it's at this accelerated test level. So how does that then correlate back to, well, I ship upwards of 20 hours, 40 hours, maybe even 80 hours potentially from a global supply chain route. So how are you telling me that 2 hour or 3 hour or even 4 hour test will simulate my whole ride? I would say, if you're really concerned about that and you want the highest level of confidence to be sure that it's going to survive that 80-hour route, there's a better way of doing it. There's a different way of doing it, which is kind of being worked on even within, or talked about within ISTA, but it's a whole different approach, that takes into consideration how much, back to the accelerated testing methodology, is what's the right approach? Do I just, if I'm really concerned about 80 hours of transport, do I run an 80-hour transport simulation? Can I run something less than that without accelerating too much? Because the risk, even on the risk to anybody, especially on the pharma side, the biologic side, is that if you over accelerate a test intensity level such that test intensity causes some type of damage to the product. And in case of biological, it could be a protein, not a bottle of water or the bottle itself that you're concerned about. But if you're concerned about the protein and you shake it so intensely that you cause damage to the protein, such that in your test intensity was so severe that that's what caused the damage, versus it would never see that intensity in the real world, that's a real risk. And so you got to be, to me, you got to think about that. It's almost like a, risk assessment for your testing. What's the appropriate testing? What's my outcome? What are the risks involved with pass fail? So, I think there are certain products that make you consider different testing methodologies than maybe the standard approach that says, I need really, really high confidence. I can't over test, and I also can't under test. I need what ISTA even used to call, back in the day, they called it the just right testing. But what does that mean? Basically, in terms of vibration, it means don't under test, don't over test. Try to dial it in as best you can, so that in the end you've got confidence that it works. And of course, when you develop these tests, what's most important in all of this is that you have some, hopefully some way to do damage correlation that says, because you're going to, it's just a pass fail test, so be it. But it's back to, you got to hopefully be able to close the loop that says the results that I see at the end of all this testing, not just vibration, drop, vibration, compression testing, I want that to correlate with what I see in the real world. If I'm shipping boxes of stuff and I have no issues with damage in the supply chain, but I test them and I see crazy amounts of abrasion and scuffing and maybe flaking of plastic particles, or the corners of my box get crushed in from whatever the testing input is. If I see that in the lab, but I never see that in the real world, you got a problem, I think. And the opposite of that is true as well. If I see problems in the field, but I'm passing all my testing, I don't have a problem with my testing. Pass it, feel good, pass the test. But I'm seeing damage in the field. There's a disconnect with damage correlation. So in the end, that's always what should be the end goal, right? Is damage correlation. But you want to do that, I think, from that idea of just right testing inputs. That's not too much, not too little. That gets you the highest confidence and addresses things like risk. Long answer again.
Okay, I'm down to what I think now is the last question.
Okay.
I guess I'm old school, but I'm used to using a machine with a deck and backboard to test single packs. That is low tech. Now that I need to buy a new machine, do I need to go with a higher tech machine?
Well, I assume that the person means they use what's called a mechanical or rotary vibration system if it's got a backstop. And that test can kind of be performed on one of these, not just ours. We make a rotary vibration machine. We make what this machine is a computer-controlled servo hydraulic vibration machine. Two different things. And we're not the only ones that make both of those types of equipment. A rotary machine is really not we would say, and anybody that does a lot of measurement and testing would say that's not vibration testing, right? That's repetitive impact testing on a rotary machine. So what happens on a rotary vibration machine, and you can do it here as well, is you set the machine for a certain frequency. It's a low frequency till you get whatever's on the table to start bouncing on the table. So you start at a very low frequency and you increase the frequency. Usually the frequency when things start to bounce with a certain input displacement is about 4 hertz, something like that, 4 to 4.5 hertz. And then once that happens, and you can actually like stick a shim underneath the whatever's being tested to prove that it's bouncing or leaving the table, you set it there and you let it run for, let's say, about an hour, or about, I don't know, over 10,000 different boom, 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 boom. That's not vibration, that's impacts. Bop, 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 bop. And it's a severe test. And if you pass it, more power to you. There's an upside to that, is that you probably have a pretty robust packaged product system. The risks, a couple of risks associated with that. One, you might be overpackaged because it's so abusive. But the other part of that is that you're not exciting it because it's just going boom, 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 boom. You're not controlling frequency energy across a broad spectrum, which is what it will see when it's being shaken or when it's moving down the rails, down the road, in the air, in intermodal transport. So there's a risk that you're not exposing it to frequencies. There's a risk on both sides, risk of over-testing and risk of under-testing at frequency ranges that fall outside of the boom, 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 boom. So yes, you have to spend more money. And again, we sell both. We can sell you either one. Now the bounce test, that mechanical vibration test, that testing technology was developed in 1940s, late 1940s, because that's about the best technology they had at the time. It's still used today, even though it was developed in the 1940s, going on 80 plus years. Why? Because a lot of people have it around the world. Why else? Because a lot of people think it works for them, and it does. It does. If you can pass the test and you have a history of using it, and you can say, if it passes this, I have proven that I have no problems in the real world. More power to you. But it's not a simulation of of anything. It's hard to kind of connect the dots on that. So like even ISTA still recognizes it in some of their lower level 1 series tests, which are non-simulation tests, but it's not included at all in something like general simulation, 3 series or higher tests, because again, you can't connect the dots. So you do have to spend more money if you wanted that higher level of sophistication. But if you want to simulate, get closer to reality, that's what you got to do. And you don't have to do it with us, just us. A lot of options for that.
Okay.
All right.
No problem. There is actually another question. So
Okay.
I'm going to ask that. When attaching additional sensors to the object, what would be a good adhesive? Epoxy, or is there something better?
A lot of options. What you want is good coupling. If you're going to use accelerometers for drop testing, shock testing, vibration testing, you want it to hold, and you don't want it to impact the, no pun intended, the measurement. Meaning that if you use double back tape, either to attach like field data recorders or even accelerometers in the laboratory, the thickness, the cushioning characteristic of that tape, if it's that kind of tape, will change the measurement, because you're going to be measuring the response of the tape, not response of the widget. It's really a response of the accelerometer on that tape. So you want a good solid mount. You know, glue is about as good as it gets, but it's glue. So, you know, if it's super glue, it can leave a residue that's a pain to get off of the base of the accelerometer. They make, just so happens, I have a little stud here. See if I can show you it real quick. Where'd you go? Oh, there it is. Now, if you can see this, tell me if you can. Yeah, so you can see I'm holding a little stud in my hand. That in this case, it's a Delrin rigid piece of plastic. That for this stud, this attaches to our vibration table, and then the accelerometer, whereas the accelerometer threads into this side of the stud, and then the stud threads into the table. So a lot of the accelerometer manufacturers make little, smaller studs without this piece here, but just the threaded insert here. So you can attach your accelerometer to this, and then you can glue this to this piece. I'm backwards in my viewing, but you can, oh, this is easier. So you can, you know, glue these pieces to the product, to packaging, without having to mess up the accelerometer itself. And even hot melt works, as long as, you know, you be careful with hot melt sometimes, because the temperature sensitivity of the sensors, they're usually pretty robust, but you don't want a big glob of hot melt, once again, acting like a cushion in some way to the attachment. So if you use it, you know, you usually try to use a minimum of it, and you push down very rigidly, so you make sure that the layer of adhesive is small enough and stiff enough that it's not changing your measurement. So yeah, adhesive is the best. For vibration testing, because we often are not shaking it so intensely, that's not especially in product testing using sine vibration, the input isn't crazy high intensity, such that it would throw the accelerometer off of whatever it's attached to. So in that case, we use glue, beeswax. We can use beeswax, and I don't have any out here by the machine right now, but I've used it here at Michigan State in the past. So beeswax is another thing that can be attached for vibration measurements. It's just not as strong. Obviously, it may become dislodged, but if you're doing testing where you're in person and can see it, it's going to be obvious whether it fell off or not, or becomes displaced, and you have the ability to put it back on. But when you're doing measurements where you can't see inside the container, or you're going to ship a sensor out in the real world and in the field, you want it to be as rigid as possible so that it's not going to fall off during the overall measurement run or shipment.
Wonderful,
That's
Eric.
it.
Thank you so much.
Yep.
I think we've come to to the end of the webinar. Just a reminder to everybody that if you need further guidance or just need some advice, Eric is available, and you can email him at eric.jonassen@pptgroup.com. And yeah, thank you so much for joining this webinar and for joining the whole series on vibration. And Eric, thank you for presenting and answering all the questions. It was really informative. And yeah, keep an eye out for the next webinars that we'll bring your way.
Thank you. Thanks for your help, Sharon, as usual. Thanks everybody that are still holding on after an hour and a half. That was fun. That was good.
That was good. Thank you, everybody,
All right.
and we'll see you next time. Thank you.
Have a good
Bye.
weekend. Bye-bye.